Michele Jamrozik, thanks so much for joining us today. We're really excited to catch up with you after meeting you recently at the IAC there in Paris. Before we talk a little bit about that conference and what you might have been doing there, tell our listeners a little bit about how you even came to be involved in space in general.
Well, since Luxembourg was really putting forth a lot of effort to expand its economic infrastructure into the space ecosystem, it really came to mind that it might be a good idea to diversify my background. And so what I did is I joined the first cohort of the Interdisciplinary Space Master program at the University of Luxembourg. And I joined it because it had really great aspects. I thought it had not only the IT, which is more of my area for space informatics and computer vision, but it also had a law component, robotics component, business component, entrepreneurship component. And so for me, that was just awesome. And that's why I did it.
So how did you end up in Luxembourg? Because I know that you were in the States originally, and then now you're abroad and working with a country that is obviously, as you said, focusing on space. And I know you have a background in, as you said, robotics as well, but let's go back a little bit earlier. So you got involved in robotics and STEM here in the States, or had you always had an interest?
Not so much robotics, but electrical and computer engineering. And I was lucky to have worked for General Motors. I'm from near Flint, and I got internships as a student. And therefore, that got me set up to have my first real full-time employment. And I ended up working in Luxembourg as an automotive software engineer.
Oh, wow. Okay. So you were working for a company here at the General Motors, and they had a branch over in Luxembourg. Right. Wow, that's really cool. So you started as a student interning in your almost near, as you said, your hometown of Flint, Michigan. So
yes.
How did you get that as a student?
Okay, so I applied, and I was really lucky to have gotten it. And I did actually, I think 3 altogether. But the first one, just applying and asking anybody And I was able to do it the first summer, and I was so lucky. And then the next summer I didn't have the opportunity. But the third summer I did. And I didn't know, actually, no, it was the first summer. I didn't even know that I could get it. So I got a lifeguard job, and I got a bartending job, and I got, I had already applied for the internship, and they all came in on my birthday.
Oh, wow. So you were a student in college then, to clarify. So you were a student in college.
Yes.
And you were applying. So you figured, oh, I'm not going to get this. That's pretty great. So it's like the lesson for our students there is you got to pay attention to what's being offered, like, because obviously it was being advertised, and then give it a shot. So that's pretty great.
Did you the co-ops.
Did you grow up in the Detroit area, or just attend college there in that area?
No, I'm near Flint. So in the Flint area rather than Detroit.
I was last in Detroit 12 years ago, and they had really revitalized. There was a real period of decline, and then it looked like the city was really trying to turn it around. Do you mind sharing what it was like? Did you ever work in General Motors in Michigan, or was all of your GM time overseas?
No, it was.
I worked for AC Sparkplug, AC West, AC Rochester. And yeah, I did work at all those companies that are pavement now.
Really?
It was kind of with coding too, right? Because I was checking out your bio. You were kind of involved on the front end. Was it programming, right? So was it involved in maybe some of the cars and the computer programming, or what exactly were you doing there?
Okay, my first internship, I worked in the plant, and I basically went around with all the different sets of skilled trades. And for 2 weeks, I was an electrician. For 2 weeks, I was a pipe fitter. For 2 weeks, I was a millwright. And it was basically to understand how the plant works and how the skilled workers interact with the production workers, interact with the management. And so that was great. I loved it. But I also realized that that wasn't what I wanted to do for the rest of my life. I loved certain aspects of it, but I'm glad that I did go on for my full engineering degree. And so that was my first experience. And then I worked also at AC West, and I worked on the F-car fuel rail system to reduce evaporative emissions.
Okay.
And I went out to the proving grounds in Arizona, and we would run testing. We went to Death Valley. We did the road trips, and that was really cool. That was quite a long time ago, obviously. but that's how I got my position in Luxembourg in the end, because I had already had these experiences
So it
in
sounds
Flint.
like the breadth of experiences you had early at least helped you make a really informed decision about the direction that you wanted to go. When did you know that computer engineering was your happy place, or software or coding, at least back then, early on in your career? When did the light bulb come on and you said, oh yeah, this is where I'd like to sort of go in this lane?
Well, I started programming with punch cards in the 8th grade.
Oh, wow, that really dates you a little bit, doesn't
It,
it?
it does. It
No,
does.
no one even knows what punch cards in. I've only seen them. I never used them, but I did see the bunch of them one time.
Yeah.
No, if
And
they've seen
then,
the movie Hidden Figures, they know. The kids know the punch cards, right? By now.
yeah.
Right.
But I was lucky to have gone to a school where one of the teachers, and I didn't appreciate this at the time, but we had basic and we had Pascal, even in high school. And this is, in the 80s.
Yeah.
No,
Early
I remember those. I was not as good at Pascal.
We didn't have those
Basic
options
didn't have a
ever.
lot of functionality. I wasn't, I don't know if I was any good, but I was at the limit of my little teacher, my teacher's knowledge then. Do you have a stack somewhere of punch cards in a storage locker somewhere with your name written on the top?
No, I
You
wish,
drop
right?
them?
Yeah, it could be museum quality. But
Yes.
actually, I'm an electrical engineer by trade.
Right.
And signal and image processing is really the area that I expanded to. But I always use software as a tool to implement my current work.
Well, let's explain that for our students. So you're an electrical engineer, and you said with imaging, right? So what is a daily, or say a weekly, what does that look like? Just to kind of give our kids an idea of understanding of how that might be different from some other engineering jobs.
Okay. Now, are we talking just, yeah, I have a PhD, so it's a little bit different. I'm a researcher.
Right.
So do we want to go lower level, or
Let's do both, actually. Let's
Yeah.
start lower level, because we do have some students who want to go the engineering route, but we will have those who will want to go into more of the academia as well, or might not even realize that there are those kinds of options to kind of go down.
Mm-hmm. Okay, so let's just start off with my automotive programming work at General Motors. Okay, so you start off and you don't know exactly what you're doing to begin with. It takes time, it takes training. And especially for a coding environment, it takes I would say about 6 months to get up to speed to know everything that you need to know how to do. Because I worked in a production environment. So that meant the software that I was working on would be the release of 200,000, 400,000 cars. And the recall potential is just such a big fear. And also the safety aspect is so important. So everything is very, very well planned and organized. And you need to meet your deadlines. There's no being late. And you need to be proactive in anticipating things that can happen that might go wrong in the future. Like, for example, we transferred chips. We went from an 8K chip, dating again, to a 12K chip, and to put inside the engine control module. And that meant that all of our release procedures needed to be updated, and somebody had to foresee that had to be done. So you have to think about these things. So I did software, but I also worked very closely with the systems engineering group, which does all the actual physical onboard electronics, and they all have to interface together. And then what I also did is I worked with the calibration engineers to develop the code. They would say what they wanted the code to do, and I would implement their wishes, and within reason. It wasn't coding like I think some kids code now, or a lot of people do. It wasn't like you can't just do anything you want. You have to be very, very careful, and you have to test every single bit of code that you write. And at the time, I wrote an assembly language. And that's a little bit tedious. And then, of course, they moved on to C. But you need to be extremely careful. And then I would check my work. First, I would verify all the work that needs to be done. If there was a change to be implemented or a new feature to be added, like I added air conditioning to a small car. Then you go through the code. You need to find every single place that it needs to be changed.
Oh, that's really, I'm just taking this in for the first time, thinking about, I'm driving a car, but I've never really thought about, you just assume, somebody puts in an air conditioning, but you're not really thinking about all that kind of background coding that goes into that. I mean, I would figure that for the safety stuff, but
Yeah, let's get in terms. If you had to reduce a modern car today to how many lines of code are in a modern car, what is your estimate?
Oh, I can't
A
even.
million?
Uh, I can't even tell you.
that's
I mean,
fascinating. I
our listings used to be this thick, and it was double paged, and it was like 8-point font or something. And I'm sure they're like,
So let me make kind of a big leap here, and you just correct me if I'm wrong. So they would have to do something like that with spacecraft as well, right? Testing for safety, making sure all that. So it seems like the background that you have with cars, it's also kind of something that we see with that spacecraft. So same kind of length, same kind of issues, or are there some differences?
well, similar issues. They're embedded systems. Okay. And everything has to be worked together. Everything has to be super verified. Everything has to be planned for. So there are a lot of parallels actually in the work that is done. And, you have to communicate with you have an onboard computer that communicates with all of your subsystems.
Right. Would you explain for the audience embedded systems and
Okay.
really the interface of software and hardware? Would you mind sharing just a little background for the people that aren't production engineers?
Okay. So an embedded system means that you have a chip inside the unit that you want to control. Okay. So here's an example, the engine control module. It's just a little box, but it controls your vehicle. It controls the amount of fuel that gets injected when you're driving according to throttle position, air temperature, ambient environmental conditions. And that information gets updated like every, so many milliseconds. It used to be 7.81 milliseconds. That's a lot of things. The main variables would be updated.
I have to ask you, why was that number chosen?
It's because of the clock rate of the chip that was used.
Thank you.
So you need something that's super important. You had to make sure that all of the code that needed to be updated and executed happened within that first time loop, 7.81 milliseconds. And then you had a 16.56 millisecond loop that was updated less frequently in a 32 millisecond, whatever. Different things had to be updated with different levels of frequency.
Got it.
So you just control your system with the embedded system.
So now you're in research. So let's talk a little bit about what the research end of that would. So you've got this background where you were learning how all the parts come together, how they're programmed, how they work, and now you are researching. So let's go to that capacity.
Okay. So I do different things in research, like what I did at IC. I'll just speak about that. I wrote 2 papers. One was about enhancing images that are collected in space so that you could determine like the pose of a spacecraft or determine orbital debris in its position, so you could eventually glom onto that and remove it or do in-service refueling. And I do that with deep learning models. So that's artificial intelligence. And deep learning just means that you have a network. And I don't know if people know what artificial neural networks are.
Well, some of our students are really into AI, but I don't know if they know what you're saying with like the specific part of the networks, but feel free to bring it down to our level if that's possible.
I'm just trying to figure out how to say it. Okay, basically you try to think of it, as synapses in your brain, right? In nodes that can communicate with one another. And if we get an input, our brain generates a response. And that's kind of the idea behind neural networks. Deep neural networks are just a whole bunch more of synapses and nodes that happen in the brain. So it's just a bigger and bigger brain.
Right.
Okay. And so that's, I guess, that's how that works a little bit. And I did another paper at the conference, and that was on reflective GPS technology. So the idea was to see if it was possible to implement the algorithms necessary to determine soil moisture on a CubeSat.
What?
Mixture.
Soil moisture.
Moisture.
So, and that's important because you can, consider drought conditions. You can consider crop health, because we've got to feed the world. right now with less resources.
Right. Is that a passive signal that would just be
Yes.
radiated up because of is it in the infrared or microwave, or what sort of wavelengths are you most interested in?
Well, it's just a passive GPS signal, so it's totally passive.
Oh, I'm sorry. You're wanting the GPS, reflected GPS signal off the surface of the earth, collect
Exactly.
that and process that, because you know what it looked like that signal did when it left the source. And
Yep.
then you can handle what attenuation for the atmosphere and all the
Exactly.
other. Oh, that's very novel, because that wave is already there, right?
Right, exactly.
It's free.
So
it's a free
it's
wave.
they call it an opportunistic signal, originally introduced by Martinera. It was originally called the Paris method, but the novelty of what I was doing was like, can we put it on a CubeSat?
Is anyone going to fly your idea?
Maybe.
How big of a CubeSat do you need to do this?
Well, we had a 1 CubeSat, so this is more or less a feasibility study. Can I even implement the algorithms necessary on this CubeSat?
It sounds like you should work with the wolf pack and let's get this thing up in space.
I know the instructor that I was working with would really love to see that happen.
That's very cool. I want to pivot back. You mentioned your expertise in signal image processing. That is very much of interest to us, not from a remote sensing standpoint, but we're trying to come up with a novel payload for an internal monitoring of a mission that involves watching a biological living thing do some digestion at a very small level. The constraint we have is we have a very small data budget for downlink. And the goal is, how do you maximize what you're learning from your experiment when you only have so many zeros and ones? Could you help us? Could you share a little bit about signal image processing and just a high level overview for the layman about what does that mean? And maybe keep in mind our interest. We're looking at growing, cells digesting, a matrix and then trying to image that. What could you share with us about that?
Okay. So in terms of, are you talking about in situ?
Yes.
Okay. So first of all, the big important thing is, what data do you absolutely have to collect? What data do you need to process? What data do you need to store? And what data do you need to downlink? Okay. So these parameters, these requirements must be carefully thought out, first of all. Then, can you be clever in terms of your data collection, in terms of onboard processing, such that you don't have to store everything and you don't have to downlink everything?
Okay.
So how can I do things the most efficiently? And I guess one of the practical things that we know in everyday life now is the compression of images, right? We have, everybody works with JPEG images. Those are compressed representations of 2D projections. And so we are able to send this JPEG data to everybody, depending on, we can choose, like on our iPhone, you take a picture and you're just out having fun for dinner. And it says, how big do you want to send it? Extra large, large, medium, small. And you decide, what quality level you want to work with. And depending on that quality level, you use a higher compression ratio. So your image quality, if you use the smallest quality, it's not going to be as good, but you're going to be able to send it more easily. So what's my purpose? How much information do I actually need to receive in order to be able to ascertain the properties of the picture that I just took? Oh, we're just having a birthday party, it's fun. Or do I need to have a high resolution image that I need to actually extract,
data,
growth patterns, or So
like
it really,
photogrammetry, yes.
Yeah, so these are the questions that have to really be answered.
That's very
in the design portion of the project, as soon as possible.
Is one last question. Do you at your level, do you ever work with okay, you take an image and then you take an image after a period of time of the same content. Do you ever play that game of we only care about what has changed so we can delete everything but, where's Waldo kind of thing? Which one of these is not like the other one?
Yeah, and so that's like the idea. This is an example. You can look up differential pulse code modulation. You look at the
You got to
differences.
say that phrase again. What was that phrase?
Differential pulse code modulation. So that's a compression scheme that you use to reduce the amount of data that you send. Also, in our videos, right, the MPEG videos, we don't send, a streaming set of 20, pictures captured at 24 or 30 frames per second. We're sending the differences between those images. We only send a new image like every 16 frames. And then in the beginning or in the middle, we send like the motion vectors to indicate how that image has changed. And so we send those along until we get to the next reference. So there are a lot of tricks you can use. And, for representing the changes, super important to realize. You don't need to send everything. You have a baseline. Maybe you need to send the original every so often, right? But intermittently, you can just send the changes and you can reconstruct a quality image.
Do you, when you talk about motion vectors, are you talking about like individual pixels or?
What they, for the, like I'm thinking JPEG here, JPEG, MPEG, they take a picture and they cut it up into blocks, okay? And what they do, what they do is perform what's called the discrete cosine transform. On that's a frequency representation of the information contained in these 16 by 16 blocks. Then what they do is in the next frame, they match that same, pattern of pixels to another place in the image. So if there's no movement, they're going to be the exact same. The differential, the motion vector will be 0. If, on the other hand, there's been change, there can be, there'll be a translation. And so you'll say this patch here, or this, pixel here used to be here. And you encode the differences. But it's not exactly a pixel by pixel. It's more of a block by block processing.
Block by block. Cool.
Is that something that you're looking on with your current research regarding the space and fraud detection? I was noticing that you're working on these kind of, currently that research is focused on AI solutions. Can you share a little bit more about that in general?
Okay, and I've got to put a pitch in for my group. I'm working for the computer vision group, CVI2, at the S&T University of Luxembourg. And my professor is Jamila Aouda, and I have to put a pitch in for her. But so the deep fake and fraud detection is basically, how all of these videos can be manipulated now, such that you don't know if it's real or fake.
Yeah.
And so what I'm working on now is trying to ascertain in more robust ways if it's a fake, because the fakes are getting better and better and better. And I also would like to get involved in educating younger people and old people in general as to how to differentiate between manipulated content. Yeah, manipulated content and non-manipulated content.
Oh my gosh, that would be a great, like a course, just for young people, for older people,
right.
The elderly,
right.
particularly.
So now you're in forensics as well, right?
Yeah. So, they're all,
Very interesting. The applications are quite broad. Very cool.
Well, I'm kind of like trying to take it all in, right? You've done a lot. I mean, but at the same time, while you've got this amazing background, you've been able to kind of hone it and keep it, with the times. And it's just kind of like that background knowledge is taking you now to this new area. Tell me a little bit about the Space Master program that you just completed and where that's at. And then we'll wrap up with the final question, which is usually just about, any advice that you have. So tell me about that Space Master program.
Okay. It was hard. It was, as you can see, I'm a little bit older, and it was a challenge, but it was a conscious decision to fill a gap, because I did have a career gap. I don't know if you know, because I had young kids when my husband suddenly died. So I had to take a break from my research, and that really hurt. That was really difficult for me. And I just did whatever I could do to keep going during that time. And then finally my kids got to the point where they were okay. And I could then start to focus on me, and I had to fill a little bit of a technology gap, because it just goes so fast. But at the same time, I've also found that even though it goes so fast, I still have the fundamentals, and I always did. And I just, not always, but since having completed my PhD, and yeah, a little rusty, but it's nothing you can't recover from. So
Okay.
the Space Master was, yeah, that is really important, because I didn't
Yeah.
have the confidence that I should have had, and probably still don't. And but it's still there, and and I have a different viewpoint on things. I can step back and look at things from a broader perspective and the utility of it, rather than just from a very pinpointed point of view. So the Space Master was really cool. I'm glad that I had the opportunity to learn a little bit more about the space law component, because that's so important in terms of space debris and liability and all that kind of stuff, that if we launch a spacecraft, we're responsible for what happens to it.
So you're
when it's up
learning,
in the
like
air.
you had mentioned earlier, like the different parts. So part of that program is getting, some kind of education on all these components of that larger industry, so that you can be well-rounded, I guess.
Yeah, and unlike like when I did my master's, I did a couple masters, and there you'd have 4 or 5 classes per semester. Here we had 9.
Wow.
So it was pretty intense. And
Wow.
And you, of
supposed
course,
to,
were working as it's in some capacity. Yeah, of course.
yeah. And so it was supposed to take 2 years. I slowed it off and did it in 3 years.
Well, what's next for you? If you could say, well, this is if I could create my own next position, what does that look like?
Honestly, I'm really trying to figure that out. I'm not sure. I hate to leave the technical. So it's combining technical, maybe with policy, maybe with, with projects. I'm really into Earth observation technologies. I really think that we need to do more to save this planet, and well, to feed the hungry world that we're going to have, and to address some of the migration crises that will follow. I want, no matter what it is, I want to be passionate about my work, and I want to be inspired by it. And I want to, or if I don't have the complete choice, then at least I want my work to enable me to fulfill my life and do something good with it.
Very well said.
Gosh, I think that's actually great parting words of wisdom. But and I really want to focus on what you said about the fundamentals. Like, we do a little takeaway afterwards, and that's where mine's going to be. I think that for our listeners, recognizing that, sure, you can keep advancing on, but if you don't have the basics is the root of all of it, right? And so if you're weak on something at the lower level, just because you've been passed on, that's probably not the best way to do it. It would be better to just have that stronger basis, and the other stuff you'll catch up to faster, as you said. I think that's really astute. For our listeners, is there any final takeaway pieces of advice that you would have for maybe students who are interested in getting into something similar, whether it's research or just by recognizing the kind of work and the ethic that you've had over all this time?
I'm going to pick up on your fundamentals. Don't be afraid to ask questions. And I know people say that and they don't really mean it. And sometimes you'll have teachers that will say that, and you ask the question and you're just flipped back. Use the resources that you have around you. Luckily, we have, online resources like Khan Academy and a lot of other resources, but find a mentor if you can. Like, I think what you guys are doing is great, because it's hands-on. I don't love the idea of education by Google completely. To me, it's a supplement. It shouldn't be a replacement. But it's really, really important that if you have a weakness, to address it as early on as possible, because you will suffer in every way. And sometimes the gap that you're thinking that you're having is nowhere near as large as it actually,
Right.
It could be tiny, but you're just missing, oh, I don't understand logarithms, so that means I can never understand what a decibel is. Fix it as soon as possible, because it will affect your self-confidence. It will affect how you present yourself. It will affect almost every aspect of your life and your happiness. And it might be the difference between you getting a scholarship and being able to really go to the best school. And it's not that really less. It's just that you don't recognize it yourself.
Because you can't see the connections, I think, at that point. I think that's really important, that's an important message for our parents to hear as well, because it's really less about, oh, look what class we've elevated to, but rather have those important foundation's been laid in order to help make those connections later.
Yeah,
Get as much hands-on as you can.
Right,
Yeah.
right. Yeah, we wrestle now with inflated grades and the perception of a child's knowledge versus what they really know.
Yeah.
So that's what we wrestle with. I want to thank you for your time. I'm going to ask you some follow-up questions as soon as we stop recording, but thank you so much for sharing about the beginnings, how you became an engineer. And thank you for sharing this wonderful content about some of the state-of-the-art things going on, especially with respect to aerospace. So thank you.
And I'm so glad that we got to meet you at IAC. We look forward to maybe working with you again, seeing you at
Yeah,
some of the
great.
conferences. We'll see you soon.
Thank you.